Okay, hi. Welcome to an introduction to Three.js and the history of open graphics. The talk is sponsored by Enovate and Opworks. So my talk is split into 6 sections. Who am I? What is a graphics API? A bit of a history of open graphics, Three.js and Webgl, and the other renderers and other options. So, first thing, take off your web dev hats, because it will take us a little while until we get back into the land of web browsers. That's kind of the nature of computer graphics. So, who am I? I'm a web API kind of Laravel developer, more back-endy, but doing a bit more full stack these days. The reason I signed up for this talk is that I've been doing little bits of hobby game development since around the mid-2000s. Such as with GameMaker, if anyone's heard of that, like playing around with C++, STL, and 2D OpenGL. Also creating maps or levels for the Cube and Celebration games. I'll mention that in a little while. At university, there was a Microsoft XNA module included, so that's using Direct 3D. We had a bit of a team project. We had a little competition. It was quite fun. We made like a cityscape, had cars driving around. It's quite interesting. Also Python and Pygame, which is actually a wrapper around STL, so it's quite familiar. It's a way to sort of easily get 2D graphics up and running. And more recently, playing around with JavaScript, WebSockets, and Three.js. And here's a recent picture. So that's me. So GameMaker is many years ago. I was about 12 or so. It's very similar to Scratch. So it's like a sort of a graphical drag you drop type programming, quote unquote programming language, where you can define your own games. So I was playing over that many years ago, and then also around then I was playing and making levels for Cube, which is a free and open source first-person shooter game from the 2000s. It came with a level editor. So when you're playing the game, you press E, and it gives you this interface with a grid, and you can select things and basically edit the world pretty much immediately. So, for example, moving floors and ceilings up and down, creating walls, and there are lots of keyboard shortcuts, but you can like select which texture, i.e., image, to have on each surface. So that's quite a fun time. And here's a map I made in 2005. The image is broken, so I've just added my own on the side. And in the description, it mentions this Cube edit mode. So before the days of Google Docs, it was actually you could edit the levels in multiplayer with other people, which was quite interesting. And here's the picture again. And here's another one. A few more points on this one. That's from 2006. Another thing I was playing around with was the Lazy Foo tutorials. So these are a bunch of tutorials for doing graphics with C++ and STL, which does a bunch of image, sound, and such related things. And he also has a bunch of OpenGL tutorials. Now this site is quite old, as you can see, but it leads me into the question of what is a graphics API, such as OpenGL, Vulkan, and Direct 3D, i.e. DirectX. So graphics APIs provide a standardized interface across GPU hardware vendors and/or platforms. But what is a GPU? A GPU is a graphics processing unit or video card. They are highly specialized parallel architecture with thousands of processing cores, unlike a typical CPU, which will have 2, 4, 8 CPUs. They're quite highly specialized and optimized for things like mapping of images, textures. So like applying the perspective transformation onto an image in a way that is computationally efficient. So you can render lots of things without your game or application slowing down. They have a relatively large onboard memory because they need to access all that data very fast. And as an aside, they also include a thing called a DSP, like to efficiently play video files. But I'm not going to talk about that. Many CPUs have a weak one integrated because they're so universally useful, even for accelerating 2D graphics, such as a typical user interface. And here's what a GPU looks like, if anyone's curious. A lot of paper launches these days. Don't quite get what's going on there. So what can you actually do with a graphics API? A graphics API allows your CPU to tell the GPU what it wants to happen. So because they are separate chips inside of your computer. So for example, you will want to do things like loading textures, i.e. images, or 3D models from your system memory into the video memory. You may want to add some model into the 3D scene at specified coordinates. You want to transform things, moving things, rotation, resizing, and so on and so forth, and applying programmable shader effects to make things look cool. So that brings you back to the lazy food tutorials. So this is tutorial number 6, using pretty much pure OpenGL. And the aim is to show an image on the screen. So I have a question for all of you. How much code do you think that this is? Any guesses?
I don't know, 30 lines?
Interesting. Any other guesses?
I'll say 31 just for strategy.
I'm going for a million.
Okay, it's between those two.
I'm going for 300. 300.
Okay.
200.
It is about 250 lines.
Oh.
And that's not
could
including.
We say 251.
It's halfway in between the two of you. But yeah, so the reason for this is that graphics APIs such as OpenGL are pretty low-level things, and this is not even including like decoding an image file, which is done by another library this person's using, dev.il in this case. So just to give us a flavor of graphics APIs, I'm going to give a little bit of a run through of some of this code written with C. Warning, this is very deprecated. This is from back in the days of OpenGL 1. We're currently on OpenGL 4.6. So first thing is to initialize OpenGL. So this does things like setting up the screen, setting your video resolution, and we set the background color to black. We turn on, we want 2D textures, and also like checking for errors. Next thing is to load a texture from a file on our hard disk into main memory. So to do that, we're calling this another image library. So that's all handled for us. That's not counted in my 250 lines. But this is this loads the actual image data, and it's calling this function in the middle, load texture from pixels 30D. And this is actually something else that we have to write. So going into that, this takes the texture from main memory and puts it into video memory as an OpenGL texture that we can actually use. So we have to define things like the width, height, and the format of the image, and a bunch of other parameters, and check for errors. Finally, we actually render it. So we go to where we want to render it, and we have to define we want to render the whole thing, and we put in 4 points which define the quad that we actually project it onto. And then finally, here's the main function. So it calls all of that, and it sets the display mode, creates windows, and does a couple other bits and pieces. So that just creates an image on a screen, because it's a relatively low-level way of doing things. This is tutorial number 6 in the series. So earlier on, here's number 3. You're just creating coloured squares. Last updated 2012. Sounds about right. So if any of you are interested, it's lazyfoo.net. It's quite old code. So that which leads me into the history of open graphics. So in 1992, a company called Silicon Graphics, or SGI, they have a graphics API called IrisGL from their 3D workstations, which are used in quite fairly well used in industry, and they rework it and release it as OpenGL version 1. And this is picked up by a number of the other graphics card vendors, so including 3DFX, ATI, and NVIDIA. If anyone's interested, 3DFX was purchased by NVIDIA in the year 2000, so they no longer exist. It's pretty much ATI now, AMD, and NVIDIA. So since 1999, we've had these two APIs pretty much fighting it out on the PC. Although OpenGL is more common for productivity applications, such as computer-aided design, i.e. CAD, and modeling software, showing simulations and such like. Here's a game from 1999 that I used to play quite a lot of. It was Game of the Year 1999. And it's a 3D real-time strategy game. So in space, so you would build some units and then tell them to do things like harvest some asteroids, or go and attack the enemy mothership. And in the settings menu, on the top left, you could choose between software rendering, OpenGL, and Direct3D, i.e. DirectX. So the two APIs have been quite well supported over the years, and games pick or choose or use one or the other. So in the year 2000, the non-profit Kronos Group is formed to manage the standard by Silicon Graphics and a bunch of other computer graphics related companies. Their mission statement is royalty-free open standards for 3D graphics, and a few other things. Their remit has expanded a little bit in the last 20 years. So in 2002, the first version of Q was released. That game that I mentioned a little while ago. It's a free open source FPS with pretty fast Quake-style gameplay. It's not particularly popular, but I will. There's another reason that I mention it, which I'll get to in a minute. It runs on Windows, Linux, and Mac. It's a cross-platform, single-player and multiplayer. It came with that level editor that I mentioned. It's a 50 megabyte download, which, well, it took a little bit of a while back then. And again, it's written in C++. So at this point, we have OpenGL as a graphics API that bridges the gap between different GPUs and desktop operating systems. For instance, you could be using Windows XP with an ATI graphics card, and you take your application and you can just pretty much move it to macOS and running a different GPU, and you don't have to rewrite your entire graphics system, which, as mentioned previously, it's quite a lot of code when you're dealing at that level. So it's good to have this standardization. However, it's only really suitable for desktops, especially as the years go by and the specification expands in order to accommodate everything that everyone wants to do, at least all of the big players. So in 2003, we got OpenGL ES for embedded systems. It's based on OpenGL 1.3, but cut down into more or less the bare minimum for what you actually need, which is perfectly fine for mobile devices. So the reason for this is also mobile devices have much less sophisticated graphics hardware, and in particular, you want low power consumption for running on batteries. But the good thing is that you can get an OpenGL ES context from within OpenGL, and that will be quite useful, which I'm getting to. In 2004, we get the first version of Cube 2, the sequel to Cube, and they now have a new logo. And on the right is the first ever map, so it's called. Again, it's just like Cube, C++, OpenGL, but it allows more advanced level geometry. So you can have rooms over rooms. The previous Cube was a bit more like the Doom engine in how it worked. You had a fixed floor and ceiling height, and you couldn't have multiple rooms. But in Sabratton, you can have much more complicated levels. If you're wondering what Sabratton means, here is some Sabratton. It's a German dish because it's a German project. Was there a question?
Yeah, sorry, Andy. My question was, is that due to OpenGL that it had more advanced support, or was that because they got a better model, like for storing the data, being able to manipulate it so they could render more?
It's the latter. It's nothing to do with OpenGL. Because a cube level is fundamentally it's an array of it's like a two-dimensional array of numbers, whereas cube 2 it's much more three-dimensional in how it works. So here's the Sabratton again, hence the name Sabratton because it's a German project. In 2005, Intel want to make an OpenGL ES tech demonstration for their Windows Mobile Pocket PCs. Now you might be thinking of these, but no, that's a Windows phone. That wouldn't be for many years after. I'm talking about these things. Did anyone have one of these? I'm curious.
Yes.
Was it any good?
Not proud of it, but yeah, I did. I think I actually had a couple of those. They were sort of, I had O2 ones, and I remember
organising meetings, more like a PDA.
Yeah, they were sort of cutting edge at the time. They used to even have like a stylus you could just sort of get out with your fingernail to then tap on it. Very, very stylish.
Kind of like the first DS.
Yeah, kind of.
So yeah, they're kind of capable little machines. So, which 3D application do they choose? Yeah, any guesses?
DirectX.
It's Microsoft. Fair point, but I mean like an application, like an actual demonstration of something that can be run.
Doom.
It's got to be Doom.
Doom is the thing with Doom is that it doesn't require a 3D API, so they want to demonstrate OpenGL ES, the 3D capabilities.
Crisis. Will it run Crisis?
Crisis does not yet exist. So here's Intel at the Game Developers Conference in 2005, and they chose Cube 1 to run on these little pocket PCs.
Nice.
And here's another one. This is an intrinsic with a 640 by 480 screen, cutting edge. So at this point, we have OpenGL ES as a layer very similar to OpenGL, where you can port your mobile 3D applications around between different devices. So you might have an Android game, and you could running on a phone with an Adreno GPU, and you can relatively easily port it to an iPhone with a different OS and a PowerVR GPU, for instance, because of the standardization in the industry due to the Kronos group. So this is interesting. What happens next? So in 2006, Cube 2 adds some GLSL shader effects. So let's see if these work. There we go. I've just added some videos because that's the easiest way to see what's going on. So you can see on the right, there's some shiny effects going on. And this is some Phong shading that we're looking at, mostly implemented via a fragment shader. So a shader is a little bit of code that you can compile and run on the GPU pretty much dynamically as you want, and as and when you want to. So in 2006, the Kronos group gained full control of OpenGL from Silicon Graphics. And the same year, Mozilla create Canvas 3D prototypes. So based on the JavaScript, like the Canvas element, they add OpenGL into the browser, and this eventually became WebGL. Opera also implemented it in 2007. Also in 2007, the OpenGL ES3 specification is released, and that brings shaders to mobile devices, again, by using GL shader language, which is the language you use to program shaders. It's roughly based on OpenGL 2, so again, you can get an OpenGL ES3 context on a desktop machine by using regular OpenGL in a special mode. In 2009, they start a working group for WebGL, including Apple, Google, Mozilla, and others. And also that year, Silicon Graphics filed for Chapter 11 bankruptcy. They no longer exist. They eventually get bought by HP Enterprise, I believe, like the remnants of the company. It's kind of bizarre. They were a really big player before them. Also in 2009, Ricardo Cabello, i.e. Mr. Doob, ports his 3D library from ActionScript for Flash into JavaScript. And here he is. In 2010, he releases it on GitHub as Three.js. So it's all beginning to come together. Also that year, he adds in a Webgl Renderer. So like when he was talking about it, he said that it's a 3D engine that can do like a variety of things, but it's quite a modular architecture. So he was able to swap out the rendering component relatively easily, which turned out to be an advantage because it's now one of the most popular WebGL frameworks that exists. And in 2011, the WebGL specification is finalized based on OpenGL ES3. So now we have OpenGL and OpenGL ES for our 3D applications that are portable between different hardware, different GPU vendors, but also different operating systems. Now, our 3D application is a web browser, and the browser provides the WebGL APIs, which we can then use in JavaScript. So with all of these layers, you can pretty much swap out everything underneath. So if you have an iPhone with a Power VR GPU, you can then move to a desktop with Google Chrome, Windows 10, and AMD GPU, and it all works pretty much the same, which is quite an achievement due to these open standards. And Microsoft Edge actually has a direct 3D implementation, which is kind of bizarre. They have a it maps the OpenGL calls into the equivalent direct 3D ones, and it actually transpiles the little shader programs from GLSL into the Microsoft HLSL. So, okay, fine, why not? But anyway, we are back. So, in 2012, Mozilla want to make an advanced WebGL tech demonstration. Can people see where this is going? So, which 3D application do they choose to port?
Cube.
Oh, almost.
Doom.
Cube 2.
Hey! So, Mozilla port Cube 2 Subratin from OpenGL into OpenGL ES, and therefore they can make it work with WebGL. And they call it, and in line with the food naming, they call it banana bread. That's some actual banana bread. Here is banana bread. So the reason, they did this for a couple of reasons. They wanted a technically demanding, fast-paced game to prove that the technology works, because there was a lot of skepticism about it at this time. And also they wanted to refine their own implementations. like in Firefox and other browsers, to make WebGL a more viable technology and to compete better with native games. They actually used a tool called Emscripten to cross-compile the C++ into JavaScript. So it is not a particularly friendly code base, but it serves as a good technical demonstration. If I get some time, I will fire it up in a while. But I've got many more slides. So in 2012, we get Opengl Es3. Some years later, in 2016, the Kronos group released the first Vulkan API spec. So this is the next generation after Opengl. In 2017, we get the final version of Opengl and the current version of WebGL based on Opengl Es3. There hasn't been any other versions since 2017, but although it's a graphics API, it doesn't really need to change a huge amount, and it's more to do with hardware support, because every GPU driver has to support every new version of Opengl, which is a relatively large amount of work. So that brings us to the present day, where we have Direct3D, Opengl, Opengl ES, Vulkan, and now also Apple Metal. So these are the lowest level graphics APIs across different platforms. And so Vulkan is beginning to come in. If you've got a modern PC, you can play Doom Eternal with Vulkan if you want. It's in the options. But yeah, Apple decided to move away from Opengl and rather go to Vulkan. They've just created their own API. So, well, Apple be Apple. And a kind of similar thing is happening with the latest version of Direct3D. It's more like Vulkan. So what were we talking about again? Oh yeah, we're talking about we were going to look at WebGL. So here's a quick jargon buster on some 3D graphics terms. A vector is a set of some number of numbers, usually 3. So it can indicate a position, scale, rotation, direction of something. They're quite flexible, but they are signed numbers, so they have direction. A vertex is a single point of a polygon. So usually it will be denoted as a vector with a vector position, and it usually has an index also. Like this is the third vertex of the your polygon mesh, whatever. A polygon is a triangle. You used to have 4-sided polygons, but not really anymore. So you have a triangle, usually part of a mesh. A mesh is a collection of polygons that form a 3D shape. A model is a collection of meshes treated together as a 3D object. So, for instance, like a gun, or a car, or an enemy, like a person, whatever. A texture is an image once you've loaded it into video memory and you have a way to use it. So it will be uncompressed at that point. So be careful with large textures. A skin is a texture which is when it's applied to a model. So it is basically wrapped around. So for this reason, you can take a standard rectangular world map, like a Mercator projection. Hello?
Oh, hello. Yeah, sorry. Quick question. What is the difference between a mesh and a model?
So a model may have a number of meshes, but like a mesh has to be a contiguous set of polygons.
Oh, I see.
That's my understanding anyway.
Like disjointed. Can they don't have to be continuous?
Yeah, so like in a model of a gun, you might have the magazine as a separate mesh so that it can move separately.
Okay, makes sense.
That's my understanding anyway. I'm only a hobbyist,
Cool.
but that's what I think it is.
It matches my understanding, Andy.
Okay, cool. Where was I? I've got to open. I have some notes here somewhere. Okay, so it's a skinned mesh is a mesh with a skin on it. So it's a model with a texture. A bone is a movable point with attached vertices used for animation. So you can move that. You have a relatively small number of bones, and that makes it actually easier to animate a model because you don't have to move around large numbers of vertices and polygons. A skeleton is a collection of bones. This is a little bit confusing because of the example that I've done, but try to bear with me. A shader is a program that runs on the GPU. So you can write your own little shader programs in languages such as GLSL, and it will compile it and run it on the GPU on the fly, even from within WebGL. So like WebGL is actually a surprisingly low-level API, considering that it's available just in JavaScript in web browsers. And a material is a shader which is then applied to a model. So you're defining how a model is rendered, essentially. So my next question is, can I use WebGL? And can I Alt-Tab effectively? What have I got? If I open a new that, there we go. So, can I use WebGL? Are we feeling lucky? Sure, why not? Interesting. I haven't seen a redirect notice like before. So, here we go. So, WebGL is very well supported. 97% global coverage. Apart from Opera Mini. Has anyone actually seen that? I've heard of it.
Yeah, I've seen Opera Mini. It was useful for compressing some data when you were downloading, and you know the data back then was pretty expensive on mobiles.
What, like back in the 2010s?
Oh, yeah, or earlier even.
Oh, okay, that's even worse. Okay, fair enough. As also, we can look at WebGL 2. So this is a bit less supported because of these browsers on the side. And also Safari, does not Apple being Apple, I suppose. But WebGL 2, you can use it from within Three.js if you want, but most things default to WebGL 1 because there aren't really that many extra features. Usually you'll be looking at newer versions of whatever library you're using, like Three.js will add features and then you just use that. Back to my presentation. Oh, good. So how about pure WebGL? So we're kind of in a similar situation as we were up drawing an image on a screen. So to write a spinning cube is 190 lines of JavaScript. I guess less than 250, but still not particularly easy to get started with. Also, you must write 2 shader programs, which is a little bit daunting. Otherwise, you get a black screen. So there's a cube that's rendered with pure WebGL, and here's an example shader. So you have a vertex shader and a fragment shader, and they get compiled in your browser and then shuffled up onto the GPU. You'll notice that it's quite a C-like language, but I'm not going to deal with that right now because this is a bit advanced, considering we just want to get started. So, to install Three.js, you can install from npm and use a bundler, as with modern web development, or you can just grab the JavaScript files from CDN. So if from the GitHub repo, you want the build folder, and then either examples.js or example.jsm directory, depending on if you want to use JavaScript modules or if you don't want to use JavaScript modules. Also, important note is that all of your assets, i.e. textures and models, things that have to be loaded in, they must be on a web server, not files on your local machine. So you can get started with Three.js just by creating a HTML file and double-clicking on it, open it in a web browser. But if you then try to load like an image that's in the same folder, you're going to have a bad time because of the way that browsers are sandboxed. You can't do that. You could put it on a local host web server, like apt install a Apache 2. It works. So that would be fine, but it must be some kind of web server. So now we have some examples. So let's make a hello world cube. It's 25 lines of JavaScript. Here's my project. I'm in presentation mode. So I have. Is this still working? Oh, there you go. Good. I wondered if my SSH timed out. So we have npm. Here's my package.json file. I can npm install to bring in my JavaScript dependencies. There are 0 vulnerabilities, which is good. And similarly, here are my PHP dependencies. And again, I can install them. And that's done. Lost my little side. I lost my little the Google Meet on the side of the screen because I changed workspaces. Right. So, example number 1. Here's our 25 lines of JavaScript. I'm going to get rid of that because I don't need it. If anyone's confused by this, my point is that you don't really need any of these tools. You can just put some files on a web server and get going. So we begin with a renderer, and we want to use Webgl. So we want the Webgl renderer, please. I'm just going to get the size of your window, and then create a renderer for that, and append it to the DOM. So this will be a full screen demonstration, but you can easily make a smaller renderer. The renderer is actually a canvas element. So you'll have a canvas element on your web page that then displays graphics. So you have you need to create a camera and a scene. So the camera defines the field of view, FOV, your aspect ratio. So you can figure that out by just dividing width by height, and you define the near and far plane. So this defines at what distance things get rendered. So we will see things between 0.1 and 1,000 units away. So what is a unit? Well, a unit is just any unit of distance that you want to use. So it could be meters, miles, snoots, inches, angstroms. The only important thing is that you keep it consistent. So once I've created a camera, I'm going to move it by just editing the Z field of it. So then that will move the camera back to position 003. In the coordinate system, the thing to note is that the y-axis is up. So x and z are north, south, east, west, if you think about it that way. So we can create a scene. We can make like a box geometry it's a cube. It's a cuboid. It's got 6 sides, and by default it will be of size 1. So we can just leave that as it is. And let's have a random color, because why not? This mesh basic material. So as I was saying before, it's a material. So we have a material that we apply to our mesh, and the basic material doesn't take into account any lighting. It will just show the color that it's got. So it will output as this color. So then we can create a mesh, and then we can add the mesh to the scene. And finally, we've got this render function. So we use request animation frame to tell the browser to call this function before it repaints, so that we can sync up our rendering and try to avoid tearing. So we want to do that every time that the browser paints, and we call renderer.render with the scene and the camera that we've defined, and that will render our scene. So how does it look? And can I switch browsers? Yeah, that seems to be fine. Right. But, don't want to catalog. You get square. Why do we have a square and not a cube? Any thoughts?
We're just looking at the front of it.
Yep. we are just looking at one side of it. So we're along the z-axis, just looking at our cube. If I refresh, we get a different color. So we know that is working. Go back into our code. I've got 1A in which I add a little bit more. So I've added this rotation code into here. So we just add 0.01 radians to the rotation vector. The way to think about rotation is that it's going around the axis as if the axis is a spindle that then spins. So if you're rotating around the y-axis, then the y-coordinates stay the same and you're rotating sideways or looking left and right, basically. I also forgot to mention, I've pulled in vanilla.js, which is 0 bytes. It's a powerful micro framework, very small. So 1A, and now we have a cube. And as I was saying, because we're using the simple material, it just outputs a color. So we can't really tell the sides apart because they're just pixels the same color. We can get a different color if we refresh a couple of times, but we can't really tell the sides apart. So for the next one, I have added in an outline. So you can create an edges geometry. So it takes some geometry that you give it, and it will give you a wireframe line around the edge. So we can then say, oh, I want to render some line segments, again with a line basic material, right, and make it white. So if we look at that cube with an outline. So we now have the basics up and running. So what next? I have my second example where I've added in some controls and lighting. So I've pulled in this camera controls. So I'm listening for events and then editing some booleans up here. And also I've also got this function, move player. So if you've pressed different keys, it will move the camera around and turn the player, which direction that the player is looking. So again, all of these angles are in radians, and all of the units are in just whatever spatial units that you want. You notice that like we are doing a little bit of trigonometry here, because trigonometry vector matrix maths does turn up quite often in computer graphics. If you remember from school, it's not what I wanted. I've got two Firefox windows. Hold back. I'll get back to this. So for that, to move the player in a certain direction at a certain angle. So, for example, if you imagine that the camera starts in the middle here and you're looking toward the x-axis, if you then rotate around this angle theta, like this O with a line through it, then to move the camera forwards in that direction, you will have to go cos theta units along one axis and sine theta units along the other axis. This is actually the z-axis. Remember that the y-axis is going up, so it's coming out of the screen from this perspective. I didn't want that. What's this? So we've got that. And we're calling this in our render loop. So this is the same as it was, but we move if needed. I've also added some code to move a light up and down. So we'll see that in a little while. The other thing I've added in is I've got a few more objects in the scene. So I've created a sphere. So again, you create a mesh with a geometry and a material, and I've changed to a Lambert material because the basic material does not take into account lighting. And again, we've got a random color. So I've arranged these at -2 x0 is by default, and x2. So that I've got a sphere, a cube, and a cylinder side by side, and I've added some lights also. So I'm calling add light here with a position. So in here, I create a point light. You give it a color, intensity, distance, decay value. So how quickly the light decays down into nothing. We add in the position we want, and then we can add it to the scene. That's actually all we need. This is not necessary, but I've included this just so we can see where the lights are. So I've just said make a sphere with a basic material, so it's white, so you can always see it, and just give it the same position and add it to the scene. So this light sphere is just a sphere that sits where the light is, and because we're in JavaScript, we can add any property into any object we want. So I've just added it into the light object like this. I believe that's all, and also on space, I've randomized the color of the cube because why not? Let's see. They're going between. Okay, that's useful, right? So example 2. I now have my 3 objects and 2 lights with the sphere, so you can see them, and also I can move myself around using the arrow keys. As these objects turn around, you can see that they're being lit, and then dark. They're dark again as they go out of the light. By pressing I and K, I can dynamically move. It was the other one. Dynamically move my lights around, so you can see that this sphere is being illuminated differently as the light moves. Any general questions so far?
No.
Okay, cool. Moving on then. So number 3. I'm going to do some more shading. So in this example, I've changed to the Fong material. So this is doing the same shiny shading that we saw in that Cube 2 video from 2006. So if I go back into Chrome, try now. You can see using some more advanced shaders for these materials of these objects. Also, we can dynamically change things as we wish. So I'm pressing space, and that's just changing the color of that cube in the middle. So we've got some primitive objects. We've got like a colored sphere, a colored cube, a colored cylinder. But unless you want to build geometry walls, that's kind of not very useful. How about we make a textured surface? So that's what I did next. Although not quite. So in this one, I have somewhere made a plane geometry. So a plane is a flat surface. It's a rectangle rather than a square or cuboid. I've given it the basic material so we can see it. Like I don't necessarily care about lighting right now. So we create it and we add it to the scene. So if we look at it, rectangle, we can move around it as you would expect. So it's being rendered in 3 dimensions. But the reason I created this one without any texture yet is because when we go around the back of it, it no longer exists. Polygons are directional by default, and this is quite useful for what's called backface culling. So if you have a 3-dimensional model, the back side of it, you won't see it because it will be obscured by the side that's in front of you. So in most cases, it's perfectly fine to not draw the wrong side of a polygon, and that can help speed things up. Actual textures, we have what we have to do is make a request and then wait for a response, as we do in web browsers. So I've created a material using loader.load, and I've given it a path, and then you can add in a callback. So when this actually loads, it will run this code. But the nice thing is that we don't have to wait for this to load before we can use the material here. So we create the plane, and we can just say, I want to use this material that we've made, please. And it will appear when the texture loads. So let's have a look at that. And there we go. So now we have a textured surface with some objects on top of it. And again, I can move my lights around. So this surface reacts to lights in the same way. And that's a textured surface. Using this texture loader, I believe that's an extra. Oh no, it is actually included. So my next example is models. So we actually want to have like a shape that we don't have to write in code. So that's what I'm doing next. And we pull in GLTF loader. So because there's many different formats of 3D models, they're all in separate files. So we just pull in the one that we want to avoid having a huge JavaScript file. So here we load a model. So the file is at this path, but this isn't actually the whole thing. It will actually load in a few extra bits, but I'll show that in a minute. So when we get the model, we go into this callback. So we put that into a variable called load model that I've defined. Interesting. Oh wait, okay, right. Skeleton. That's what I'm thinking of. So skeleton model is set to this, and I'm going to call this function. I also scale it down a bit because I noticed it was very large the first time I loaded it in. I also create an animation mixer. So this model is animated, and it comes with animations. So we want to optimize them, and this is just a fix for like it was running for slightly too long, and we can add that. We can add the model to the scene at this point now that it's all loaded. One other thing, in our render function, we need to tell the animation mixer how much time has passed so that it can go to the correct keyframes. So this clock.getDelta is this is just the time that elapsed since the last time that you called it. So this helps keeps things running on the clock rather than slowing down if the frame rate goes down. I've also got a frame rate meter, but that's quite simple. Here. You have a model. And it looks kind of like it's all one color, but it does actually have a texture. If I go into the inspector, you see that this model it defines a couple of other files. So it loads the GLTF file that we defined, but it also loads this bin file and the texture. So here is the texture. And as I was saying, it gets wrapped around all of the meshes in the model. So if I refresh that, and in my example, I've also defined some key press events. So if I press 1, 2, 3, 4, then I can do some animations. So if I press 1, we get an animated skeleton. And 2 stops it. And then 3 runs a different animation. So it has a number of animation tracks that you would call in different situations. For example, if you're being attacked, you'd play this one. If it's just moving along, you'd play this one. Mixer can also mix the two together, which is kind of interesting. So it averages all of the points of the different keyframes and just tries to put all of them together, which kind of doesn't make sense, but it's interesting that it does that.
Never seen a breakdancing skeleton.
There you go. One other thing with the way that I've loaded this, when I load it, I just add the model to the scene as is. So like we've got this model coming in from the loader. How do you add more than one? It was actually a little bit involved. or it was a little. I had to sort of figure out how to do that. So my next example is the same thing, but with 2 skeletons. So I've defined 2 of them here, and in this method, I'm using this skeleton utils to clone the entire model, because that's apparently a non-trivial thing to do. The skeleton utils is another thing that we have to pull in. It's a separate unit of code. Where was I? So,
Andy, are they going to animate separately? Like, is it mutable, the clone, or is it an immutable clone?
it does a really deep clone.
Yeah.
So I've got 2 animation mixers, and they animate independently. So when it loads, I've just said start the second one playing animation 2, and also move the first one over to position of x minus 3, and add them to the scene. And like before, we have to update both of the animation mixers with the amount of time that's gone past. So if I open this one, we now have 2 skeletons, which animate separately. And if one, I can animate this one. And note that the animations aren't running in sync. They are completely independent, even though I'm running the same animation on both of them. And here's our breakdancing skeleton. So, can I get back to my presentation? Yes. So, how about a game? Let's say some skeletons appear and run forwards. You can shoot the skeletons. If they reach the end of the platform, you lose. So that's in number 8. So there's a little bit more code in here now. So I've got a few more lights and a few more bits and pieces. I've got a textured floor here, so I've added 3 of them just to make the floor longer and so that it doesn't stretch. Like you can actually make it this. It doesn't have to be the same aspect as your texture. It can be very wide and thin if you want, and it will stretch it out. So got some more lights. I have a new model called like the pistol. Both of these models, by the way, I found on Sketchfab. They are Creative Commons. How you do 3D modeling is a whole other subject. The amount of work that goes into 3D games is quite large. If anyone else wants to talk about 3D modeling, that's maybe another talk for another day. So when it loads, I am. So there was a bit of a bug with the way that the bone animations work and like the culling. So like due to the viewing frustum, because things are moved, it doesn't quite take it into account. So I've just disabled culling for the gun. I'm setting the pistol animation to be paused, so that it's just sitting there. And I've made this add skeleton function. So I want to have 5 skeletons at these positions, and I'm adding some more fields onto the cloned skeleton, because you can just add and set things as you want in JavaScript. So what happens is that it plays the first animation, which is the kind of jumping out of the ground, and I've set it to loop once. Clamp when finished means that it will stop. Like, it doesn't keep looping the animation. That's kind of redundant. That doesn't need to be. 1 is a default. And this is just some notes about what the animations are. I keep going. So now in the render loop, we now have to update all of our moving objects. So we've got a bunch of skeletons. So for every skeleton, as before, we tell the mixer how much time has gone past. I've got, if there's an animation, well, if there's not an animation, then make the skeleton to be moving. So moving is a field that I've defined. So i.e. when it finishes spawning, then start moving toward the player. If it's moving, then move the skeleton along a little bit. And this is just a little thing, like if they fall off the edge, then make them go downwards. So .y is the vertical position it will go down. And similarly, we can update the pistol animations. So I should have here we go. So when you press space, if the pistol is not currently animating, then reset the animation and play the animation. And I believe that is all of it. Yep. Okay. So game is number 8. Seconds. And there's my gun. And I can shoot. So then if we just wait a little while. Also I randomized the Z position so they're not running in line. And now I lose. Because they reach the end. So now we have a kind of interactive application. I'll play this again, and I actually shoot a skeleton. Notice that there's a problem. Happens. Because I've forgotten something. So the problem here is, what are we looking at? What the hell am I looking at? Is the line from the film. This is from Spaceballs, by the way. They're watching a VHS tape, and they're getting very confused because they see themselves. And that's kind of spoilers. I recommend Spaceballs. So what I'm talking about here is, if you have some 3D scene with some objects and a camera, if you're looking at this, you can see that the camera is pointing towards the cube in the middle. But that is a relatively non-trivial thing to actually work out in computational terms. What we need to do to figure out what the user has clicked on, or what the user is looking at, is have a line coming out from where the camera is and figure out what that it actually goes through. And this is not exactly easy. It involves some maths and geometry. But thankfully, Three.js provides us with a class called a Raycaster that we can use for this. So back into PHP Storm. Here's the final game. So let's just find what we want. Here's the Raycaster. And it includes a method called setFromCamera. And this vector that it takes is usually used for the position of the mouse on the screen. So it's how far up and down on the screen that you are. But 0, 0 is the middle. So we just pass in 0, 0. And then we check for every skeleton that we make a collision box, and we check, does the ray intersect the box? If it does, then we set these fields moving to false. Dead is a field that I've defined, make that true. And animation stop, please. What skeleton dead does is, in our update function, got if skeleton dead, and we are manipulating some of the bones. These are skeletons, but these are animation bones I'm talking about. This is a little bit confusing. So I actually missed this from my. Oh, that's not helpful. Let's try that again. Print, right. I want Chrome with my demos. I actually missed this. I think it was number 6. Ooh, 7. Okay. So in this one, you can access the bones. So if we do this on the JavaScript console, the way that GLTF files get loaded is that you get a big hierarchy of things, which is why I've got all this .children. So if you do .children, there's like a 3D object there, object 3D. So we go down this structure, and we can find bones. Here's a list of bones. We can get bone. And they're helpfully labeled. So this one is called skeleton rig root joint. I'm not sure if we can see that. Let's make that bigger. That's better. So if I get bone 5, it says neck skeleton rig. If I get number 8, that's shoulder. 4, jaw, sure. Do dot rotation, and then manipulate it. So if I do plus equals 2, you can see that the jaw turned around in a quite painful looking way, I must say. Let's try a different one. Arm upper L. Okay. You can see that his arm moved up now. And I can do that again. There we go. We can make him wave. Okay. So I'm doing that in my final example. You'll see what happens when a skeleton is dead. I believe that's all of it. I've covered all of the rest of this. Just having a final look. Yep, I believe so. Okay. The final example is here are skeletons. If I miss, nothing happens. If I shoot a skeleton, he's dead, and now he's also sulking. Interestingly, you can. I lost, but you get the point. So it moves the neck down, so he's sulking because he's dead. Sure. I'm gonna give that another go. So, there we go. All of them. And that's all of my demos. So, any questions about all this code, Neil?
Andy, are you launching a game called Americans versus Skeletons or Skeletons versus Americans?
It would seem so.
You should. The last game was amazing. For anyone that didn't see Andy's last game, he built a board game because during the pandemic he couldn't get to his board game, and he built it in Three.js, and it was amazing.
Yeah, I might show that in a little while. I'll have to go into my server and reset it. I have a couple more slides, so let me finish off. Let's see. Oh, I've got another about 5 slides. Not too many. So there are other renderers also that don't use WebGL. So there's the CSS 3D renderer. If I copy this. Sure, that's fine. So here's a periodic table. It's all moving around, and we can look at it in 3D by clicking and dragging. But the interesting thing is that if we inspect this, we can grab these individual elements. These are actually regular DOM elements. And what's happening is that Three.js is applying computed CSS 3D transforms. We should see it. There we go. Transform, translate, matrix 3D. So it's calculating the numbers that need to go into that function to move everything around nicely. And similarly, it will put it into it can put it into a sphere. There you go. Also, there's the Svg Renderer, which was one of the earlier ones. Can I copy the link? Let's open it here. It's a bit strange. It doesn't seem to have. It doesn't render things in the right order. Like there's things behind things that are being drawn. But here's an SVG that's being rendered. So like it's got some 3D geometry, and it's just calculating which positions to put everything, to draw everything with as a scalable vector graphic. I assume it's doing some kind of software rendering to just move everything around. But yeah, so that's the other renderer that you can use if you want. Slides. That's presenter view. There are a few other things to mention about Three.js. It's good for getting started, but it's not a game engine. Once you understand the ropes of like all of this 3D stuff, you should consider a more fully featured one, such as Babylon JS, which is in the browser, or Unity or libgdx, which both of those have HTML5 WebGL exports, so they will cross-compile into JavaScript and let you create like a browser version of a game. The reason I say this is that there are things missing from 3JS, like collision detection. There's no easy way to figure out if two things are colliding. Like, have I hit a wall, for example? There's no physics engine. There's no path finding. So if you've got an enemy that's chasing you and you go around a corner and there's a wall or something in the way, then you need some way for the enemy to figure out, oh, I've got to walk around the wall. And that's relatively non-trivial. So 3JS is only really for the rendering side of this. So that's why it's not included. Also networking. So, but you can add your own JavaScript libraries for these things. So, you can give it a go and see what you think. There are other use cases other than games, of course. So like various types of 3D diagrams, like scientific or medical diagrams, architecture, maps, like engineering. You may want to have some animated 3D diagram showing what's happening, and you don't really need any interactivity. So that's it. Just having a rendering is perfectly fine. Fallout 4 and 76. Good point. And things like simulations. You can also, if you've got an existing web page, you can apply gimmicky effects to it using the CSS renderer. Why not? And one final note from the future is that WebGL will eventually be replaced by WebGPU. This will only really happen once OpenGL itself is deprecated, because WebGL is a series of bindings into OpenGL ES. So once all of the graphics hardware is moved towards Vulkan, Metal, and Direct3D 12, then we will be in WebGPU territory. But that won't be for several years, most likely. In Google Chrome, you can turn on WebGPU if you want in the experimental section. So if you go to Chrome //flags # enable unsafe WebGPU, you can turn it on, and that's what you see. And that's the end.
Right.
Anyone have any questions?
Too many. Too many.
I'm sure everyone has lots of questions. But like 3D like game development is there's a lot of moving parts. It's a lot of work to make a 3D game.
Yeah.
Application.
Where's the bridge between obviously what he was doing is quite imperative in style, like which obviously it was for a demo, but like are there for just, even like with rendering like demos, stuff that you can do with 3JS, like are there like toolkits on top to help make it like more decorative, or is it?
What do you mean by decorative?
I suppose like anyone like framing the animation, like you define what it should look like in any given state. Rather,
You mean declarative, not decorative?
yes, sorry, to clarify.
No, it's cool. I was just trying to work out if I was missing something.
What you mean, like rather than imperative, like you add stuff to a scene? I mean, how? What kind of?
I suppose like
What do you want? You mean like SQL is a more declarative language?
sorry, I mean like I suppose like the React or Vue.js equivalent of what you're doing.
Well, there are more full-featured game engines like Babylon JS, and there's you can see a bunch of examples on their website.
React.js does have one, Andy. So it's not core React.
I have heard about React. There's some. Is there a 3.js plugin?
So basically,
Or is it WebGL?
It pulls in. I think it's WebGL, but it renders through 3JS because nearly everything does.
Yeah, lots of things are built on top of 3JS because it's because of those things that are missing from 3JS, as I mentioned.
Tim wouldn't need to do a lot of what you did. However, you probably wouldn't have animations unless you took over, like made a higher order component. And I actually think that would make it harder to think about. Even though it would look like DOM, you would have to do all the hard work to make like the state, the use effect bindings, and you'd have to define your own. Maybe someone's written some that you can pull in, but eventually, as with all React, the day one benefit starts to slough away.
Yep. There are many examples on Three.js.org. And okay, this is like many of them have a little button that will tell you the code. But not that one apparently.
I'm glad this was an intro to Three.js and not like advanced Three.js. Because
Yeah, it's a massive rabbit hole. There's so much. Yeah, so here we go. Here's an example. So they've all of these examples just have code available that you can look at. But yeah.
Awesome,
Oh,
dude.
I was
Pretty good.
gonna mention banana bread. So how good can WebGL be? Let's have a look.
WebGL over Google Meet.
Yeah.
Yeah, I thought it was the examples lagging, and then I realised Google Meet is what's lagging.
Yeah, that sounds about right. High resolution. Okay, this is not quite as cool as I remember. Isn't there another one? Mozilla kind of disowned it after a while. It's like they don't really have it on their website.
Pushing the limits of what? It's the third link down.
Here we go. This is what I'm looking for. So, lava chamber. Sure, that's a nice one. It has like glowing lava, and it takes a while to load, as you can imagine.
Could this be used for background in Google Meet for more comic effect? Like you said, it's in a canvas, so I'm imagining that we could.
Yeah, you can pretty much put anything in there. I should use. One other thing is that Chrome has a better implementation of WebGL than Firefox. That's why I'm using Which is why I was using Chrome for things. But yeah, like a canvas, you can put anywhere in a web page, really. When you say a background for Google Meet, do you mean like
Like what Andy's got. He's got himself some fruity friends.
Yeah. There's ones that move.